Hello and welcome to my channel. Here with me Ziad Snoussi. Today we are going to discuss an optimization problem and solve it using a genetic algorithm. Okay, so we have this maximization problem here. If x will be equal to x squared, it's a function of a single variable. We have two-dimensional problem here, which is x design variable or decision variable x and f of x. Okay, and x, it will be take only a primitive value for x. It will be from 0 to 31. Okay, so we need to find x to make f of x as maximum as possible using genetic algorithm approach. Okay. Terms of genetic algorithm. In this discussion, I am not going to go into details about the terminology. Just I need to focus on the implementation of genetic algorithm to our optimization problem. So I need to pass quickly through these terms. First, we have the chromosome. Chromosome is string solution. It means the solution to our problem in form of genetic algorithm deals. Okay. So it takes the encoded form or binary form or some octal or hexadecimal form, okay, that the genetic algorithm deals, okay. And we have gene is bits. Any part of the solution or part of the chromosome is called genes, okay. Gene. The genotype is the encoded form of the solution or design variable. So it takes, in this case, we have a binary form. Also called chromosome. It's also in some textbooks find it individual, okay. And the phenotype is the form of the solution or form of the solution in the model form that the model deals, okay. So in our case we have a mathematical model, so the phenotype will take the decimal form, okay. And that's it. Let's proceed ahead to go to solve our problem. Okay, so now first step, we select initial population at random. So we choose, for example, population of size 4 here. Okay, it could be any number. It could be selected depending on the requirement or application. So one can select 6 or maybe 8. As I said, it's depending on the application. Second step, we obtain the decoded x values for the initial population generated. So we take the first string here and we find the decoded value and all other strings here and find all the decoded value. I'll show you how. For example, if we take the first string, so we take first string here, this one, which is 0 0 1 1 0, and find the decoded value or decimal value for that. So 1 2 3 4 5 bits. One, 2, 3, 4 plus the final one. This is the most significant bit, so we have the 0 times 2 to the power of 0, and the second bit, which is 0 times 2 to the power of 1, and the third 2 to the power of 2, and so on. Sorry, 1 here, and we have here 1 2 to the power of 3, and the final one, which is 0 2 to the power of 4. Okay, so we got here 0, we got here 0, we got here 4, and we got here 8, and here 0. So this plus this, we got 12. So this is the decoded value for the first string, and we make this process for all these population, and we got the decoded value x. Okay, and step number 3 will calculate the fitness or objective function for the entire population. So we just evaluate this x values here into this function, and we got this fitness or objective. Okay, we evaluate 12 into this, we got 144, and so on. So, and we calculate the sum for that for later calculation, and the average, and this is the maximum value of this number. Okay, step number 4, we compute the probability of the selection. this is the equation for using the probability of computing the probability. You take the fitness for each chromosome and divided by the summation of all fitnesses in the number of population. In this case is 4. So just use this formula to compute this column here. Okay, and we compute the expected count using this equation here, fitness over the average of fitnesses. Okay, and after that you round these numbers to find the actual count for these 4 strings or 4 chromosomes here. Okay, we use probability, expected count, and actual count to this gives us an idea which strings or chromosomes participate in next steps. I mean crossover operation using roulette wheel selection. Okay, so this gives me an idea which chromosomes from these will have a good opportunity to go to the mating pool or go to crossover. Let me show you a little about my Matlab code here. I'll leave it in the next video, and we will discuss with each other the Matlab code step by step in next video. Okay, so just let me go through it quickly. Here we have for example, I made a quick program. So in this example I made quick Matlab program which take 4 strings or 4 chromosomes randomly, and it's not repeated, and find the encoded value. It's the binary value. Be careful here, this is the most significant bit of this one. Okay, and this is the fitness for each chromosome, and I plot this 22 with 484, sorry, this, and we have all these points. So this is X and this is Y, these numbers. So in this case we have 4 chromosomes, which is the red star here. So which one has the good opportunity to go to the crossover operation? This and this and this. Okay, so this chromosomes is a good solution, is the best, because it has the great fitness, the maximum fitness, because our optimization problem is maximization. So we are looking for the X value which gives me fx as maximum as possible. So this chromosome has is a candidate to be a solution, and is to have a good opportunity to go to mating pool and go for crossover operation. I hope this point is very clear for you, why we select this chromosome, because its fitness, it has a great value here. This one I think is 23 here, and has 529. Okay, this is not the same numbers as our example, but I need to illustrate the idea. So if you can see here the probability of the first chromosome, which is 0.1247, it comes from, as if you use this equation here. So the probability of the first string here, we take the fitness, which is we are talking about this string or this chromosome. Its fitness is 144. It's over the summation of all fitnesses, which is here in this equation, which is 155. We get 0.1247. Okay, and you compute the same operation for all other chromosomes. You see the summation of probability should be equal to 1. If you multiply each probability multiplied by 100, you will get this number and get this number, and so on. The total sum is 100. Okay, and as I told you, the probability is equal to the fitness over the summation, and the expected count will be equal to fitness over the same numerator, but the denominator is the sum here, and this is the average of fx. Okay, if you put these numbers in the percentage probability into this circle or this roulette wheel, each with the suitable area. For example, this one takes this pi, and this takes bigger one, almost half of the circle of the roulette wheel. You see how this chromosome, the second one, this chromosome, which is 25, solution, this one has a great area here, almost the half of the area. So if we spin this wheel, and if it is stopped randomly, if we have some arrow or something, and this wheel is rotating, and after that it will be stopped, so this arrow will be pointed this area, has a great opportunity to point this area, at least for example 2, because it's half of the area, half of this area is reserved for this chromosome. Okay, if you round this expected count properly, for example, if it is bigger than, for example, let me write it here, if it's bigger than 0.4, for example, if it is above 0.4 will be rounded as 1, and if it is below 0.4 will be rounded as 0, and so on. So this will be rounded because it's bigger than 0.4, it will be rounded 1, and this because this fraction is below 0.4, so it's rounded as 0, so we have 2 here, okay, and so on. We compute the actual count for each of the chromosome. Because this chromosome has a good or big probability, percentage probability, so it will be appeared twice in the mating pool, and this will be appeared once in the mating pool, and this will have a poor opportunity to go to the mating pool, so it will not be showing in the mating pool, and this one will be appear 1. So this will be appear only one time, this will be appear twice, and this will not appear, and this will be appear. Okay, this one has a good this good solution. It gives me 625. Okay, as I said, we have this will be appeared twice in the mating pool, the crossover operation, and this will be appeared only once, and this will be appears only once. Just keep these, the first, second, and the fourth one will be go to the mating pool. Okay, so this is the mating pool. We form the mating pool based on the actual count. As I told you, this one appears twice because it has the best fitness, and this appeared 1 and this appeared 1. Okay, so we make crossover between these two parents, and then make and produce 2 offspring, and make a crossover between these 2 parents and produce another springs. Okay. The crossover point specified as single point. I'll use a single point crossover, and new offspring is produced. Okay, for example, if we use this is the operation of crossover, by the way. If we take a single point crossover, we take this point from parent 1, and this point, the same point, will be in the parent. So this part and this part. So the first children will take this and this, and the second children will take this and this. This one of the children, or this one takes this part from the parent B and this part from parent A. So we got the first child or offspring. It's called in genetic algorithm term, this one. Okay, so in our case, from these, which is I think the 0, yeah, the first one here and this one, and we take this point first, this one, this area. So this part and this part for child number 1, child 1 will take 0 1 1 0 1, and second child will take this first part from parent 2, which is 1 1 0 0, and this 1 0. Okay, these offsprings called. Okay, why we take this it's not a fixed rule. It could be here or here to make this crossover. It's randomly, and there's no fixed rule, and there's could be make it in many ways. Okay. In the same way, this crossover appears. Don't. I think there's a mistake here. Maybe this is the first one. After first bit. This after second bit, maybe. Okay. Don't worry about this. Okay. Okay. So the mating pool, we make a crossover between these two and produce these two childs. Okay, as I said, as I write here. Okay, and these two make crossover between these, and we get this. Okay, so we compute the decoded value for each of these chromosomes. So we make a crossover operation. We get a new children or offsprings, and this offsprings, and we decode each of these binary string into decimal value, and we compute the fitness for each of these. So as you can see here, these two numbers have good fitness. This one has a good fitness, and this has a good fitness. So these two chromosomes, this one and this one, it looks like that we don't need to make a modification on that. So because this is a candidate for the solution, and maybe we don't need to make a mutation process on these. Okay, but these are poor solution because it gives me small number and fitness. Because if you can just, I need to illustrate the idea here in Matlab graph. For example, the poor solution like this one or this one, if you make mutation on these, it will may jump to here and will give you a good solution. But we cannot rescue and make the mutation on that because it's not guaranteed to go this way. It may go this way. Okay, so just poor chromosomes make mutation on it. Okay. Okay, this is a mutation table. Mutation operation. So this is the mutation table here. Mutation operation is performed to produce a new offspring. So we just need to use a bit flipping. This is a mutation means. So we need just, for example, this, we need to leave this one and this one without any modification. So it will be still. There's no flipping, no mutation on these. So this why we represent all zeros. So there's no change in any of these bits of this crossover of this chromosome. This and this will be still the same. So this will give me, this will be mapped directly to this one. This will be mapped directly to this one. This is why there's no bit need to be flipped. Okay, but the first one here, as we said, because it's poor, gives me poor fitness, so it is a candidate for the mutation. And mutation position could be randomly, could be change any bits for these. So because it's the most significant bit should be changed. This the means of this string or this binary value here. So this means the most significant bit should be flipped. So it was this one, it's the same, and this one should be flipped to 1 because the first bit here tell me this one should be changed to 1, and this goes to this. Okay, same way this way, this bit should be flipped. If it is 0, it will be goes 1. If it is 1, it goes to 0, because the position for this manipulation process here tell me this should be flipped. Okay, or complement. Okay, after that we compute the fitness for each of these new offsprings here. Okay, we decode all these x values here. Sorry, in this mutation I mean, we decode these values. We decode these values to this and compute the fitness. Okay, this will complete one generation for this genetic algorithm. So from these tables, from these three tables here, the selection, crossover, and mutation, we can observe how genetic algorithms combine high performance notation to achieve better performance. Okay, if you can see, the population average fitness has improved from this number, the average for the first, the average fitness here from 288, let me write it down here, from 288, the average fitness, it is improved to this one, 636. Okay, so the average fitness has improved, has maximum value now, and the maximum value has improved from 625 to 841 during the same period, which is the first generation for genetic algorithm. So the improvement of this algorithm can be seen successively. This only the first generation. Okay, I hope the idea is very clear now. As I told you, in the next video we'll be demonstrating or discussing the Matlab code for implementing the genetic algorithm for solving this problem. I hope you find this video helpful for you. If you have any question, please leave it in the comment section below. I will be very happy to help you, and thank you for watching. See you next time.